Thousands of years ago, a little white and yellow flower lived in the Arctic tundra, blooming under the feet of Ice Age giants like mammoths and woolly rhinos. This little flower belongs to the genus known as Dryas, and it's still around today, thriving in cold climates like the Rocky Mountains, Alaska, Iceland, and Sweden, although those giant megafauna sadly are not. But for a brief time, about 12,000 years ago, these flowers could be found all over the northern hemisphere, from New England to Central Europe. So how did this little cold-loving flower wind up in places that we associate today with warmer climates, and for hundreds of years? Well, at the time, those places weren't warm. After the northern glaciers reached their maximum extent around 20,000 years ago, the planet started to warm up. But then, something happened. And that something sent the world into a cold snap that lasted about 1,200 years. For example, in the Channel Islands of Great Britain, it may have gotten as cold as negative 20 degrees Celsius, whereas today it rarely drops below 9 degrees. This cold spell was so intense that geologists have given it a name, the Younger Dryas, after those little flowers that flourished in the newly cold climate. And yes, in case you were wondering, there's also an older Dryas, which was a shorter cold event around 14,000 years ago that lasted only about 200 years. The thing is, during the Younger Dryas, it didn't just get cold. This chunk of time also coincided with one of the largest mass extinctions in recent history. So for decades, scientists have been studying the cause of this event and trying to figure out if something like it could happen again. And it turns out that what caused the Younger Dryas and the extinction of the megafauna are both the subjects of heated debate. In the late 19th and early 20th centuries, experts started finding fossils of Dryas flowers in places where they didn't seem to belong, like Denmark and the southern UK. And they actually uncovered 2 layers of these fossils, representing 2 separate cold spells, the older and then the younger Dryas periods. Now, you can't find these flowers there today because it's just too warm for them. So, since these flowers could only have lived where it was cold, the fossils suggested that this part of Europe had returned to a more tundra-like state. And in more recent decades, more evidence has been found to support this. For example, in ice cores from Greenland, experts have found chemical signatures that are consistent with a period of much colder temperatures. And in the UK, scientists use fossils of insects and plants to estimate a temperature range for their Channel Islands. And they found that the warmest month was between 9 and 13 degrees Celsius, which is the same as today's winter temperatures. But while the evidence gave us a sense of what happened, that there was a sudden cold event that allowed an Arctic environment to expand south, it doesn't explain how it happened. And figuring out the cause of the Younger Dryas has been hard. There are lots of different hypotheses, ranging from changes in ocean circulation to volcanic eruptions and meteorite impacts. One suspected culprit is the planet's flow of water between oceans. You can think of it like a conveyor belt. Oceanographers call it the Atlantic Meridional Overturning Circulation. This flow of ocean water starts near the equator, and when the warm water moves north, some of it evaporates, which makes it saltier. It also cools down as it moves toward the Arctic, releasing its heat around Western Europe. Both of these processes make the water more dense, and density is what's behind all of the movement of the conveyor belt. If this circulation pattern slowed down, the northern hemisphere would get a lot cooler. And that's actually the premise of the movie The Day After Tomorrow, if that helps you, where New York freezes over, albeit on a much shorter timescale. But what would make this system slow down? Well, some scientists think that the Younger Dryas happened because of a dam made of ice in Arctic Canada that held back a huge glacial lake suddenly collapsed. In this scenario, a lot of glacial water ended up in the North Atlantic Ocean, and because that water was fresh and not salty, it was less dense than the seawater. That density difference messed up the whole system because water sinking down to the deep Atlantic is a crucial step in the ocean conveyor belt. So when that part broke down, it made the circulation slow down or even stop completely. Then the warm water got stuck near the equator, so there was no heat transport to Europe. And experts have found evidence of that meltwater in the form of a specific isotope of oxygen in sediments north of Alaska, dating back 13,000 years, which is around the same time as the beginning of the Younger Dryas. Now, we know that the sudden flow of meltwater made its way all the way to the Atlantic, so the fact that it originally came from Alaska suggests that this wasn't just like a trickle, it was a huge amount of water. And what's surprising is that this vast amount of meltwater was probably there in the first place because the ice sheet on land was melting due to a warming climate. So it's possible that warming actually drove the Earth into a mini ice age, which sounds weird. Now, another hypothesis is that the Younger Dryas was caused by a big volcanic eruption in Germany, which we know happened around the same time by radiocarbon dating the deposits that it left behind. Now, the direct effects of such an eruption on the climate would have only lasted a couple of years, like maybe some cooling caused by sulfur particles in the atmosphere reflecting sunlight. But it could have had indirect impacts that lasted much longer by causing changes in ocean circulation or the expansion of sea ice, or both, which in turn cooled the North Atlantic. So far, experts think that it's possible that an eruption triggered the Younger Dryas, but they're still running computer models to figure out how it all worked. And maybe it happened alongside the meltwater event. Then, in 2007, another possible cause gained traction: a major meteorite impact. This event could have unleashed that flood of meltwater. In this scenario, sometimes called the Younger Dryas impact hypothesis, an asteroid at least a kilometer wide hit the Earth around 12,900 years ago. Ow. But evidence of this impact remained elusive until 2018, when geologists discovered a crater buried under Greenland's Hiawatha Glacier. Early data show that it could be associated with the Younger Dryas. And in addition to the crater itself, researchers have found chemical signatures of an impact all over the world. For example, research from South Africa has found a spike in the element platinum in layers dating to before the Younger Dryas. Platinum is rare on Earth, but it's more common in meteorites, so the rapid increase in platinum could be the chemical footprint of some celestial impact. But the case isn't closed just yet. To figure out if a giant impact really caused the Younger Dryas, we need to confirm how old that crater in Greenland is. Also, much of the chemical evidence is still heavily debated. One thing scientists are sure about is that there were major changes to ecosystems taking place during the Younger Dryas. At the same time as this cold spell, an extinction event wiped out many large vertebrates in the Americas, Europe, Africa, and Asia. By the end of this period, 36 genera of megafauna went extinct in North America, including ground sloths, saber-toothed cats, and other iconic animals of the Ice Age. Now, most of these extinctions happened at the same time as the cold event, but that doesn't mean that the cold was the only factor to blame. There are a few different ideas about how and why so many vertebrates disappeared. Some experts thought that the most important factor was hunting by humans. This model was developed in the 1960s and is called the overkill hypothesis. But archaeologists weren't convinced. Why would people around the world start overhunting megafauna all at the same time? There is some limited evidence from one beach in Canada that people were hunting horses and camels some 13,300 years ago. In addition to the bones, archaeologists also found a nearby hunting trail with footprints of mammoth, bison, and other game animals. And there's evidence that people hunted 4 other kinds of megafauna at different sites in North America. But the timing isn't quite right. Some genera of megafauna went extinct before humans even arrived in North America. So even though there are some signs that point to hunting so long ago, the more popular analysis of the extinctions says that they were caused by multiple factors, including humans and climate. And while a lot of research has been focused on the extinction of the megafauna, there's plenty of other evidence that shows that lots of big changes were taking place. For example, fossils in Hall's Cave, Texas, showed that the diversity of animals and plants there dropped during the Younger Dryas. And even though Texas is a long way from Greenland, cooling occurred simultaneously in both places. The landscape in Texas changed from forest to grasslands, and some big herbivores like bison and 2 species of horse disappeared for good. But other animals just shifted their range. Hall's Cave shows that warm-adapted hares were present before and after the Younger Dryas, but not during the cooling period itself. And hares were part of the story on the other side of the Atlantic as well, where members of the Natufian culture were living in the southern Levant. These people hunted animals like hares, gazelles, deer, tortoises, and partridges. And based on isotopes found in deep-sea sediment cores, it took only 20 years for this region to cool significantly, which had major impacts on both the people and the environment. And in response to the colder temperatures, human society became more mobile. People had to move around more because they couldn't rely on the habitats that used to sustain them. Finally, after about 1,200 years of cold, the Younger Dryas period just ended. And because there's no clear answer as to what caused the Younger Dryas, it's hard to know exactly why it ended. But based, again, on sediment cores, we know that the ocean conveyor belt started to strengthen again about 400 years before the period ended. And it's still unclear why there was such a delay between changes in ocean circulation and the climate of the Northern Hemisphere. Despite this lag, it took less than 100 years for this weird episode to finally end, which is really fast by climate standards. In fact, we know that temperatures in Greenland rose by up to 10 degrees Celsius in just a few decades, or less. Now, the events of the Younger Dryas might seem dramatic to us, or even unique, but this was actually just the most recent event of its kind. There were many climate changes before the Younger Dryas that were just as abrupt. This one has gotten more attention because it happened at the same time as these other big biological changes, like the extinction of the megafauna and the movement of human populations. As temperatures warmed, the Dryas flowers retreated back to their current habitats, and much of the world went back to its previous state. But many of the megafauna were gone for good. Ultimately, what we're still learning about the Younger Dryas might help us better understand the larger history of Earth's climate and of living things. To me, it's nothing short of astonishing how much we can learn from a simple little flower.